the examples of Frankel defect. Here we have a silver bromide ionic materials, and as we mentioned, what's the Frankel defect? That means we have a pair of vacancy and corresponding interstitials. That means the silver ions jump or diffuse to interstitial site to be an interstitial defect and left a vacancy here, and this kind of defect we call it as a Frankel defect. But Frankel defect actually can be like the silver jump to interstitial site or bromide jump to interstitial site. Both of case, or that means either the cation or anion left its original site to jump or to move to the other interstitial site. This phenomenon we call it as a Frankel defect. So in this case, in silver bromide, from experimental observation, we find that is cation silver diffuse or jump to interstitial site by interstitial C mechanism. So in this case is the cation silver jump or diffuse to interstitial site and left the vacancy here. So now we can try to write down the equation is before the formation of Frankel defect, the silver ion is at silver site with neutron charge. And after formation of Frankel defect, now the silver ion is at interstitial site and with one positive charge and left a vacancy at silver site with one negative charge. And based on this equation, you can write down the K equilibrium. The rate constant for this equation can be write down the vacancy fraction. The interstitials fraction times the vacancy fraction equals to exponential minus Frankel defect formation energy divided by KT. And based on the knowledge we learn is based on the charge balance, the concept for charge balance. So we know the numbers of silver ion at interstitial site must equals to the vacancy at interstitial site, right? So to reach the electrical neutrality, we know this equals to this, so you can get the atomic fraction of silver at interstitial site equals to vacancy fractions of silver at silver site and equals to exponential minus Frankel defect formation energy divided by 2kT, because if this one equals to this one, then you got this square, right? So you can get the atomic fraction here, and the numbers will be the same, so you can get these results. So next, as long as you know the fractions, then we can try to write down the self-diffusivity for silver and bromide. So the self-diffusivity for silver, the cation silver, is equals to, because this is ionic material, so we put the G here, and would be what? Because the silver actually is obey the interstitial C diffusion mechanism, so it would be the atomic Xi is atomic fraction of silver at interstitial site. Di diffusivity for these interstitials and correlation factor, right? So, and for bromide ion, this anion So would be also is a ionic material, put a G here, and the bromide here. The bromide is a big guy here. The only way to bromide to diffuse through vacancy mediated mechanism is through vacancy at silver side, right? So is XV is a vacancy fraction at silver side. Diffusivity of bromide diffuse or jump to the vacancy at silver side and times correlation factor F. But some people probably will ask, Professor, this bromide is so big. Is that possible to bromide to jump into this vacancy with a small size? Yes, it's possible, but we believe the diffusivity is very small, right? Okay, so as long as you can easily write down this, so you can try to formulate the first part is the atomic fraction for these interstitials, right? Is the what is a Frankel defect formation energy. Then we separate them in entropy term and enthalpy term. Diffusivity of this interstitials of silver ion, so would be the migration energy of this cation move to interstitials, so also separate them in entropy and enthalpy term. And the coefficient part actually is because this is FCC, so it's A squared F and mu, which you can check in the section 1 in these lectures. And regarding to this part, we just easily write down the XV. So is what is a vacancy fraction at silver side. So it's also the Frankel defect formation energy divided by 2 and separate in entropy and enthalpy term. And the diffusivity of bromide would be this one. Is a migration energy of this bromide and ion jump into the vacancy at silver side is a migration energy term. And the rest of part is, as we mentioned, because it is ion materials and it's FCC. Okay, so based on this, you can simply get the first term is temperature independent term, and the second term is temperature dependent term. So the temperature dependent term, you can find the exponential inside the exponential term. The upper portion is we call activation energy, included the Frankel defect formation energy part and also the migration energy part. And as we mentioned, if you are interested in or you want to know the diffusivity of the cation or anion in your developed materials, you can measure the D star, self-diffusivity for cation at different temperature, and you take a log after fitting, you can easily get the diffusion activation energy for cation in your developed ionic materials. Okay, this is the most important. This slide we are going to discuss the self-diffusion in extrinsic ionic solids. What is extrinsic ionic solids? Now we have a potassium chloride, and inside this potassium chloride, you can observe the Ch4 defect formation in this one. So when you, based on previous slide, we know that the self-diffusivity for potassium is proportional to vacancy fraction at potassium side, right? So if we want to manipulate the diffusivity of potassium ions, that means you can either increase the diffusivity or decrease the diffusivity. What we can do in your experiments, the most easier way is change the vacancy fractions at potassium side. So So in this case, we are going to dope the calcium chloride in potassium chloride ionic crystals. So we are going to dope the potassium chloride. So if we dope the calcium chloride into the potassium chloride, so let's try to write down the chemical equations here. Is the calcium with 2 positive charge, right? So when you dope this one inside the calcium chloride with Ch4 fats, that means in this potassium chloride, there are lots of pairs of vacancy, right? So the calcium ion is going to sit or locate at where? At potassium side. And this is with 2 positive charge. And this vacancy actually was 1 negative charge. So that will you sum it up, so you will find there should be 1 positive charge at this potassium side. And the chloride, we got 2 chloride in the meantime, right? So chloride is occupied like chloride side, so with neutron charge. And the other chloride is also located at chloride side, so will be also neutral state. The electron state will be neutral. But as you know, the generation or production of this vacancy defects is as a pair. So as long as you generate 2 vacancy at chloride side, then there must be 2 vacancy at potassium side. So you only use the 1 calcium to occupy 1 of the potassium side. So you are going to left 1 vacancy at potassium side. So this is why we got this equation. And don't forget, based on these results, you know, as long as I increase the doping amount of calcium chloride, then we will get more numbers of vacancy at potassium side. Okay, so in order to reach the charge neutrality, so all the positive charge should be equals to all the negative charge. So we have positive charge one is the calcium at potassium side, and also the vacancy at chloride side also with 1 positive charge. And the negative one, only what we have is a vacancy at potassium side with 1 negative charge. So this is the equation we are going to have is based on the charge balance. So this will be reach the charge neutrality. So based on this, don't forget, as long as you dope these materials into the potassium chloride, they need to obey this equation. What we learned from semiconductor theory is the concentration of Vk with negative charge times the the vacancy fraction at potassium side with negative charge times the vacancy at chloride side with positive charge would be equals to before dope the vacancy fraction at potassium charge square. So it's something like the P times N equals Ni square. Ni is the intrinsic carrier, the charge carrier. So this is what we learned from the semiconductor theory. So based on this equation, we can substitute this by using this equation. So we will get Vk minus the calcium at potassium side with 1 positive charge. So it substitute as this one. So we got this equation, and we solve what's the Vk. is a vacancy fraction at potassium site can be expressed like this. So based on these results, we know as long as we want to get the vacancy fraction at potassium site, as long as we know this one, right? Then we can formulate the diffusivity, self-diffusivity of potassium in these doped ionic materials. So based on these results, it can be simply you can simply divide it into two cases. If the VK prime pure, before dop, the vacancy fraction at potassium site is much larger than this one, the doped concentration of calcium chloride, then this one is quite large. So you can ignore this one, drop this term out, and you only have this term, take the square root of it and times this one, right? So you drop this term out, and what you get is the vacancy fraction at potassium site will be equals to the vacancy fraction at potassium site before dop. The pure means before dop, right? So this kind of situation, we call it its intrinsic properties. Okay, but the other case is, so in order to be, as long as we know this, we just use this result to substitute this XVK, then we can get the self-diffusivity of potassium ion can be expressed like this. This dV is migration energy, and the first term is related to what? How to get the VK before doped will be based on, because the Ch4 defect, so it will be equals to Ch4 defect formation energy, what we derived in previous slide. And the other case would be if this VK prime is much smaller than this one. So the results, this value will be very small. So we can directly drop this term out, and you got this 1 plus 1 is 2. So the VK prime will be equals to the concentration of the dopant is the atomic fraction of calcium at potassium site with one positive charge. Actually, this is related to how much calcium chloride you dope in this ionic materials, right? So if it is correct, you can get the diffusivity, and this will be the XVK will be the equals to this value, right? Is the atomic fraction of calcium you dope, or calcium chloride you dope, and the dV will be the same, related to migration energy and correlation factor F. So this is what we learn is we can separate into this, and this we call it extrinsic, because the diffusivity is dominated by the concentration of the dopant. So we call it is extrinsic properties or extrinsic ionic materials. Okay, so that's next we are going to learn about how this self-diffusivity of potassium change with temperature. So we take the log on both sides and draw the log d k star versus 1 over t. So we are going to get two slope, right? The first slope will be this green with, because the energy, the temperature dependent term will be Hs over 2 formation energy, Ch4 defect formation energy over 2 plus the enthalpy, migration enthalpy divided by it's only migration enthalpy, right? So this slope actually included the k, so it's Hs over 2k plus Hm over k. Then you can, this is and the other one is if you extrinsic one, because this is the concentration, it's a no concentration, because you always know how much calcium chloride you dope in this ionic material, so this is the constant. And the temperature dependent term will be only this term, so the slope only associated with the enthalpy, migration enthalpy divided by K. Okay, so this slope must smaller than this slope. Okay, so based on this, you know, one thing is at the higher temperature region, this region, the self-divisibility dominated by intrinsic property of ionic materials. And with you decreasing the temperature to lower temperature, then the divisibility of this ionic material be dominated by extrinsic properties, which means it will be dominated by the concentration of the dopant you dope in these ionic materials. So this is all the story about this. But now, if you have, but in your experiments, probably you just have a doped ionic solid. What you can do to get the energy term? Usually what we are interested in would be the energy term. If you have a doped potassium chloride, then you can directly measure the divisibility of potassium ion as a function of temperature. Then you probably will plot this, you will get this curve, this black curve. Then after fitting, you can fit as this slope and this slope. And based on this slope, you can get what's the value for vacancy migration energy. As long as you know this one, then because you also can fit this, you get this slope, right? This slope you minus this term, then you can get the Schottky defect formation energy. So if you have the doped ionic materials, then by doing this kind of experiments, then you can get two information of your developed materials. Developed ionic material, doped ionic material is vacancy migration energy and also the Schottky defect formation energy. That's how we then we can, by using this kind of method, you can know more about your doped materials or your developed materials by just measuring the decay at different temperature. Then you need to add the fitting, then you can get this value. As long as you get this value, then you can get the Schottky defect formation energy of your materials. Okay, so today just ended here.